Give this a second to think about it. Okay, so entropy. So remember, entropy is the one that deals with disorder, the randomness of our world. And so they're essentially, if you have a positive delta S, then you are increasing disorder. So the biggest things we're going to be looking for would be going from a solid to a liquid to a gas, becomes more disordered. Solid, liquid, gas. From fewer moles to more moles. And then from a smaller container to a larger container. Another one I'm going to throw in there just for fun. A compound is more ordered than a mixture. So those lists would always be like negative, going this way is negative, going this way is positive. So far, so good? Questions on that? Can't read something?
Ooh, do you
want to turn off light?
I
think it's the window. It's the window.
Yeah.
Oh, that was worse. You can't turn off the windows. I don't think that makes a difference, but go for it. This is one of the reasons I got a smart board.
I'm just not sure if that will show up in the recording.
I can see it. Okay, so can I explain the S what? Solid, liquid, gas. Sounds great. And then it's only half of the argument or the battle or whatever you call it. So we're moving. I actually feel like that's worse. Maybe it's now because it's dark. I hate it. Now I look weird. Thank you. Okay, so enthalpy is the other part of the discussion, and that's going to deal with the energy in terms of heat of your reaction. And so that's where we use our delta H. So remember, your delta H being negative is going to be an exothermic reaction, which means heat is a product. Heat is produced. And delta H being positive, then would be the opposite. It's endothermic. And heat is needed, so heat is a reactant. That glare's still okay? Or whatever. Does that make it worse? What I just did turning lights on? So that kind of talks about how entropy and enthalpy work separately. Do you have questions on that at all? So then let's talk about the concept here of delta G. There's two ways that you know to calculate, well, there's lots of ways to calculate delta G, but the two big ones we talked about, one of them being delta G is equal to delta H minus T delta S. And that equation you're more likely to use just in terms of helping us identify what the sign of delta G will be. Remember, delta G is what controls spontaneity. If you have a reaction that is spontaneous, your delta G has to be negative. So delta G is always going to be negative in a spontaneous reaction. Whereas delta G has to be positive then if it's not spontaneous. Or remember, spontaneous, thermodynamically favorable means the same thing as spontaneous. It's just a lot more words to say. delta G. So anytime you're asked about one versus the other, just kind of know those go hand in hand. If I write here, can you guys see it okay? Okay, so then what we're gonna say is we're gonna take delta G, delta H, and delta S and see how the three work together. Delta H and delta S control delta G, how those two work together. And so you essentially have like just a few choices. Delta H and delta S can both be positive. Delta H could be positive. Well, let's say they could both be negative. Delta H could be positive and delta S could be negative. Or delta H could be negative and delta S could be positive. So essentially those are your choices. It's going to be one of those, right? So if they're opposite signs, it's always either going to be positive or negative. And so for me, one of the things we've talked a lot about during the year is the fact that when delta H is negative, that's more likely to be spontaneous because that means your reaction's exothermic and a reaction's much more readily going to give up energy than take it in. So we know negative delta H is more likely to be spontaneous. Well, positive delta S is also more likely to be spontaneous because you're moving towards disorder, and that is going to be more likely to happen naturally. So when this happens, your delta G is always negative. So that tells me that you're going to always be spontaneous. And I would argue, sorry, there's only so much space, that you want to try to memorize this one. And if you memorize this one, you can kind of balance everything from there. So far, so good. Questions about why that is what it is? Pause so you guys, can you see everything? Do you need me to read something for you? Okay, so if we know negative delta H and positive delta S is always negative, then the opposite, we're going to guess, and no, has to tell me that delta G is going to always be positive, which means these reactions will always be not spontaneous. Positive delta H, negative delta S, always going to be positive. Your reactions will never be spontaneous. So then if they're both positive or if they're both negative, now you have, it's going to fluctuate depending on temperature. So if your values are both negative, then your delta G will be negative only at low temperatures. And I think it's kind of nice that it's both negative because if you think about it, negative temperatures are low temperatures. So that can kind of help you remember that when they're both negatives, it can only be spontaneous at low temperatures. And then if they're both positive, it can only have a delta G at high temperatures. This chart is definitely something you would like to have memorized for your test in some way, shape, or form. We're going to use this kind of based on that equation. I know 4th hour, several people wanted to take a snapshot of it, so I can wait for a second if you guys want to do that with your camera. Or it's online, you can screenshot it later. Questions on anything here?
So is temperature measured in Kelvin or does
Yes.
it matter? Okay.
Temperature would be measured in Kelvin. We'd probably give it to you in Celsius and you'd probably convert it. But it would matter though, because if you had it in Celsius, then a negative temperature could really mess with this whole system. Here.
Is positive delta S, is that more disorderly?
Correct.
What is considered a high temperature?
You would probably be told this reaction is happening at a high temperature. One of the AFL questions, I think, said it's spontaneous at low and not spontaneous at high or something like that. So probably you wouldn't have to guess.
If delta S is positive, why is it more likely to be spontaneous?
Because the definition of entropy is the idea of moving towards disorder. And so moving towards disorder is more likely to be spontaneous. I'm not sure. I feel like I'm answering your question with your question, but are you good with the idea that entropy is disorder? And so if you're increasing disorder, then you're increasing entropy. So So you're making a positive delta S. Does that help? Okay. Anything else delta S, delta H, or delta G related? Yes.
So all the examples you have for the water for delta S, those are all positive.
Right. Yeah. Talking about moving that way is going positive.
Yes.
Okay, then I'm going to erase this, and I'm going to move on to galvanic versus electrolytic. How's that sound? Okay. So question for you. When you say you want me to compare the two, I could either just make like a chart, left versus right, or a Venn diagram or something like that kind of comparison, or do you want me to draw those cells and just sort of walk through? Kirsten, would you say? A table? Want me to do a table? Electrolytic versus galvanic? Is that kind of what you were thinking? Drawing.
You just walk through it and then have us see if they can change the picture.
Yes, that's what I was asking. Which one is it that you're looking for? You want, how many people want a picture? How many people want a table? Ooh, that was close. All right, we'll try to do both. We'll see how that works. Okay, so it's hard to like walk through them at the same time. So I probably won't. Okay, so far this is going to be my galvanic cell. I'm going to add to my picture as we go. So for your galvanic cell, a couple things that we know about. Is it spontaneous or not spontaneous? So I know my delta G has to be negative. What should my cell potential be? Positive or negative? Positive, because the goal of a galvanic cell is to produce energy. So we want to have a positive E value. Remember, those should always be opposite each other. Yes, sir.
So the cell potential is just like the prediction of how many volts the cell has.
Yep, that's exactly right. So then, because this is a galvanic cell and I'm not actually producing any energy, then here in the middle, I'm going to have a voltmeter that'll just measure my volts. We'll figure out what number should go in there in a second. Okay, so then we're going to pick, these are two beakers. In order to set it up, I've got my two metals. Now in a galvanic cell, because this happens spontaneously, my two metals here are going to control the flow of electrons. So what metals I put in there are going to decide which way the electrons go. I'm going to pick metals. Does anybody care which ones we pick?
Ag and nickel.
Okay, so I just labeled the two. Now I'm going to go to a reduction potential chart, and I'm going to look for their two values. So if I find my chart, Ag plus 1 electron equal Ag solid. And then nickel, Ni plus 2 plus 2 electrons. Ni solid. So Ag's, I forgot to write, was plus 2. Okay, so I just pulled these two values off of my reduction potential chart. You'll always be able to have those. You're never going to have to memorize any of them. So between these two, now the question is, because the metals are the ones that are controlling it, which way are the electrons going to flow? Between these two, since this is based on a reduction, which one is more likely to gain electrons? Good. So this is going to become my reduction. And so it has to be, because always, regardless of what it is, the cathode. So then this one is going to be my oxidation. And so you need to flip this reaction around. And that is always true. You will always flip your reaction for your oxidation one. And so then remember, when you flip the equation around, you're going to change the sign from being positive to negative. Yes, Kelsey?
And so the reason the blue agent is more likely to be reduction is because it has like a smaller positive charge.
The AG had the higher positive charge.
Oh,
Yeah, so remember the one that's going to be reduced is always going to be more positive. And so in this instance, well, in our galvanic cell, more positive here. And we're looking at, what was I going to say? Oh, so since we've said silver is going to be our cathode, it's the more positive of the bunch, and so it's going to pull the electrons to it. And nickel is going to be my anode. It's the more negative of the bunch, and it's going to send the electrons away. So now my electrons are going to travel this way from nickel to silver. So far, so good? The question would be, how many volts can they make? So now I'm going to combine my equations. I have 2 electrons here, but only 1 up here. So I am going to double this reaction, but I don't change my E value. And so then my electrons can cancel, and I'm going to add my 2 values down. So what's my cell potential?
1.0.
So now I can say up here, I know this number is going to be significant figure-wise. I'm adding 2 numbers that both have 2 decimals, so my answer should have 2 decimals. You're going to want to round it because you're going to think, well, that had 2 sig figs and this had 2 sig figs. Remember, in addition, it just matters the place. So 2 decimals, 2 decimals, 2 decimals. Well, I have it showing like electrons are flowing, but obviously they couldn't because I'm missing something. What are we missing? Yeah. So we need to put in a salt bridge. And a little tiny salt bridge here. And we also need to include actual solutions. So I'm going to fill my beakers up with some solution. Oh, I should probably put my salt bridge under my solution. Otherwise, it wouldn't be very effective. All right, so this solution on this side has to contain what ion? Got to have an Ag ion. But Ag ion can't get into solution all by itself, so we have some sort of negative that goes with it, and we'll pick nitrate's a great one. Doesn't have to be. So if somebody else tells you you're going to have a solution, you can go with it. And here's nickel. So on this side, I have to have a solution of nickel and then some other ion. You probably pick nitrate, but it could be anything. Maybe it's sulfate. Maybe it's chloride, whatever. Okay. I'm using it as an example of like if I told you it was nickel sulfate or something else that you could believe me that happens. If you had to come up with your own, I would pick nitrate. And I'm just trying to use something different so you're not used to it only being able to be nitrate. Yeah, nitrate would be the one I'd want you to choose.
For every reaction?
Yep. Well, for every galvanic cell reaction, I guess. Anytime you don't want a reaction to occur. And then in the salt bridge, we need to choose some other ions to put in there. And once again, you want to pick ones that are not soluble. So we're going to have K plus and NO3 minus. What did I say? I'm sorry. I did this the other day too. You want them to be soluble. That's the words I'm trying to say. You don't want them to react, I think is what I'm wanting to say also. Both. Because you need the compound in there to dissolve, but you also don't want this compound and that compound to react. So the goal would be that everything stays in water. Somebody here have a question? Okay. So far, so good? Great question. So next up, Lily, do you have a question? Let's talk about how our ions are going to move around. Joey, do you have a question?
I was just asking about if you had a voltmeter, wouldn't that change? Like if your volts were negative or positive, just depending on which direction the electrons would flow. So that's what we were doing
On
on
the,
the
on my.
Oh, yeah, like if you hooked it up wrong, your voltmeter would think your electrons were flowing the other way.
So if we draw it in on the wrong side, that'd be wrong. Okay.
It's fine. So far, so good? Okay, so salt bridge. So then, knowing which way the electrons flow is important, but also understanding where the ions are, how they move, and why they move is going to be important too. So if you remember what's happening in this reaction, it's key to our overall reaction. So our Ag plus ion is going to be gaining electrons to become Ag solid. And so these Ag ions that are here are going to be attracted to the Ag metal. And those electrons that are coming in this way, they're going to all join up together, and we're going to get a buildup of Ag ions. And so this cathode here is actually going to weigh more at the end of the reaction, because the silver ions that were in solution are going to gather with those electrons and become solid on the piece of metal. Does that make sense? So over time, all of these silver ions are going to leave solution, and you get a buildup of negative ions in that side. So now your cathode solution is negative. That would be a problem. We need to always have neutrality. So we have to get rid of that negative ion, and so it gets attracted to the salt bridge, and the potassium ions get attracted to the solution. And so they get pulled together, and the key word, like the buzzword you would use for that, is to maintain neutrality. Because you need both sides to be equally positive and negative, basically be neutral, to increase that electron flow. So remember, your salt bridge's role is to provide a way to complete the circuit and let those ions transfer from one side to the next. So here your solution is the one that's reacting. Really, it's the solution that's reacting with those electrons, grabbing them up, and it's negative.
Can you repeat the bit from like when the Ag is like becoming built up on the cathode? I shouldn't fix that.
Okay, so I think I started with, so the Ag ion here
Yeah.
has to meet up with the electrons here. And so then we have a buildup of Ag solid. And so my cathode gets heavier. And then that leads to the solution becoming more negative because it loses the positives. And so since it's negative, the ions in the salt bridge get attracted, and the ions in the solution get attracted to the salt bridge. Abby, does that sound like I probably said what you wanted me to say?
Yeah.
Okay. So far, so good?
So do they go in the salt bridge?
The nitrate ions will go into the salt bridge, and the potassium ions will come out. You'll probably be asked more likely, like, will the potassium ions go out? And that's mostly what's happening. So far, so good. Okay, so it's not only going to happen on one half, it's got to happen on the other half too. So then remember here, my nickel solid is getting turned into nickel ions. So this piece of metal is going to come in here and create these Ni+2 when they send off its 2 electrons. And so now this nickel metal is actually going to get smaller in size due to the reaction. So it loses mass. And the ions go into solution, and now you're going to get a buildup of positive ions on that side. So here your solution becomes positive on the anode side. And so my negative nitrates that are in here and my nickel ions here are going to switch places again. So the nitrate will be pulled into the solution, the nickel can be pulled out of the solution, once again, to maintain neutrality. And it's important that you kind of recognize that flow of electrons, or pardon me, flow of ions. What questions do you have? Yes, sir.
So when all the ions swap places, is that like the battery dies?
Yeah, eventually you'll reach equilibrium. And so at equilibrium, where all your ions have moved as much as they can, let's just pretend like that says equilibrium. Remember, delta G is equal to 0, and so you have a dead battery. Yes, sir.
I get that the electrons go from nickel to silver because of the standard reduction potential. But why do you have it marked as negative? It isn't like a charge of 0.
Is what a charge of 0?
The anode.
No, the anode itself is more negative as compared to the cathode. Because here, remember, it was the more negative of the bunch, and this is the more positive of the bunch.
Is
That's-
Ni 0?
You're thinking of the charge of the metal itself.
Yeah.
But when we connect Ni to Ag and we put a salt bridge, we're allowing for electron movement. As soon as you connect them, they are going to naturally move in the direction of giving up its electrons. And so it's going to, as soon as you connect them, start giving its electrons away. And we know it's the one giving the electrons away because of its reduction potential.
So you may have already gone over this, but could you explain again how delta G changes through the reaction?
Delta G in this reaction starts out negative, and it would stay negative through your reaction, but as it gets closer to equilibrium, it moves closer to 0. Once it gets to 0, your reaction stops, and your reaction's at equilibrium.
So like in terms of delta H and delta S?
You don't need to know that. Here, if you were talking about delta G in this situation, the other equation, delta G is equal to negative NFE, is going to be the one that's more likely to come about. N being your number of moles of electrons, F is Faraday's constant, and E is your cell potential. You have that equation on your equation sheet, you just have to know how to use it. Okay, so that's, what?
Is F given?
It is. Delta G, oh yeah,
It's like just delta.
just delta. Kara, what?
Then what was like, delta, what would that, like exactly what you saw before that?
Delta G?
Yeah.
Yeah, how spontaneous it is. More negative, more spontaneous. Less negative, less spontaneous. Yes, sir.
Can Colin take his test?
Yes, I was just gonna say that. I'm gonna pause for a second and get him started on his test before we start electrolytic. And if you guys, we're gonna start cutting into your time.